In this lesson, you will learn how sequences are described, classified, and summed. You will also connect sequence formulas to real situations such as seeding, growth, and loans. It is a long list, but fortunately sequences enjoy standing in an orderly line. Most sequence questions fit into 4 broad jobs: generate, recognize, predict, or accumulate. Before calculating, decide whether the question asks for one term or a total. Mixing up these two is the mathematical version of ordering one slice and receiving the entire pizza. A sequence is an ordered list, so both the values and their positions matter. You can also view a sequence as a function whose allowed inputs are the natural numbers. In a sequence, cutting in line is not permitted. An explicit formula jumps directly to any requested position. A recursive rule starts from known terms and builds forward. Explicit formulas take the elevator. Recursive formulas prefer the stairs. Substitute the indices one at a time. The factor -1 to the power n alternates the sign, while the added n shifts each value. Alternating signs are a sequence's way of changing its mind every term. Arithmetic sequences repeatedly add the same amount. Geometric sequences repeatedly multiply by the same factor. Always check several consecutive pairs. One coincidence does not earn a sequence a membership card. For Part A, subtract consecutive terms. For Part B, divide consecutive non-zero terms. Part C begins like a geometric sequence but then abandons the pattern, proving that first impressions can be mathematically misleading. Both formulas use n-1 because the first term requires 0 moves from itself. Arithmetic motion uses repeated addition, while geometric motion uses repeated multiplication. The first term refuses to commute to work. The common difference is -5. Substitute it into the arithmetic general term formula, simplify, and then use n equal to 25. Checking n equal to 1 should return 8. That quick check catches many off-by-1 errors. Each term is 1/3 of the previous term, so the ratio is 1/3. The exponent is n-1 because the first term has not yet been multiplied by the ratio. This sequence shrinks quickly, like free time during exam week. The off-by-1 error is common because n looks more natural than n-1. Test every proposed formula at n equal to 1. If it does not return the first term, the formula has already failed its opening audition. A convergent sequence settles closer and closer to one finite value. It may never equal that value exactly, because limits care about the destination more than the parking spot. A constant arithmetic sequence converges. Any non-zero common difference sends the terms upward or downward without bound. Arithmetic sequences are consistent, even when their long-run plans are questionable. The absolute value of the ratio controls the size of the terms. Ratios with magnitude below 1 shrink toward 0, while ratios above 1 grow. Negative ratios add dramatic alternating signs, because apparently magnitude alone was not exciting enough. In Part A, a fixed numerator divided by a growing denominator approaches 0. In Parts B and C, compare the absolute value of the ratio with 1. Part C changes sign and grows, which is not exactly the definition of settling down. Writing that a sequence tends to infinity describes unlimited growth. It does not mean infinity is a number sitting at the end of the sequence. Infinity is more of a direction than an address. Sigma notation compresses a long addition into one symbol. The lower and upper limits tell you where the index starts and stops. Sigma is basically a very efficient accountant. Expand the sum by substituting every integer index from 1 through 5. The expression generates the first 5 odd numbers, whose total is 25. Sigma notation saves space, but it does not do the arithmetic while you are not looking. Both formulas calculate the same arithmetic partial sum. Choose the version that uses the information already given. Good formula selection is less work, and mathematics fully supports strategic laziness. First calculate the first and 30th terms. Then apply the arithmetic sum formula using the average of the first and last terms times the number of terms. 30 additions have now been replaced by one formula, which is an excellent trade agreement. The geometric sum formula applies when the ratio is not 1. If the ratio is 1, every term is identical and the sum is simply n times the first term. The sign check prevents the formula from turning into unnecessary algebraic drama. The ratio is 1/2, so use the finite geometric sum formula. The result is less than 24 because the infinite continuation would approach 24. The sequence keeps contributing, but increasingly tiny donations. A fixed numerical change indicates an arithmetic model. A fixed percentage change indicates a geometric model. Dollars added and percentages multiplied may sound similar in a sentence, but their long-run behavior is very different. The row sizes increase by a constant amount, so the model is arithmetic. First find the final row and then sum all 20 rows. Even the back row deserves to be included. It paid the same ticket price. A 3% increase means multiply by 1.03 each year. Because the initial population is assigned time 0, 10 years corresponds to exponent 10. Percentage growth compounds quietly and then suddenly acts surprised by the result. Indexing depends on whether the initial value is labeled 0 or 1. State the convention before substituting. One small label can shift every answer by an entire year, which is impressive power for a tiny subscript. The remaining examples use the same formulas in reverse or in applications. The main challenge is identifying the unknown and choosing the correct relationship. The formulas have not changed, they are simply wearing different costumes. Treat the final listed value as a sub-n and solve the general term equation for n. The answer must be a positive integer because a sequence cannot contain 41.7 terms. Fractions are welcome in the sequence, but not in the head count. Use the geometric general term and solve for the exponent. Recognizing 2187 as 3 to the 7th power makes the calculation immediate. Powers are much friendlier when they introduce themselves. This time the sum is known and the common difference is unknown. Substitute all known values into the arithmetic sum formula and solve the resulting linear equation. The formula works perfectly well in reverse. It has no preferred direction. Each partial sum creates one equation involving the first term and the common difference. Solve the two equations together. Then use the recovered sequence to find the 20th term. Two sums are giving you two clues, and neither requires detective sunglasses. Dividing two geometric terms eliminates the first term and isolates a power of the ratio. Once the ratio is known, substitute back to find the first term and then calculate the sum. Division removes the mystery faster than a lengthy interrogation. The multiples of 6 form a finite arithmetic sequence. Identify the first and last multiples in the interval, then solve for the number of terms. Listing all the multiples would work, but the formula would like an opportunity to justify its existence. Because the total number of seats is known, use the arithmetic sum formula with n unknown. The resulting quadratic has two roots, but only the positive integer can represent a number of rows. A negative row would be architecturally ambitious. The population changes by a fixed number, so use a linear or arithmetic model. Solving for t gives 6 years after the beginning of 2025. Always translate the elapsed time back into the requested calendar year. A percentage increase produces an exponential model. Logarithms isolate the time exponent, and the result must be rounded up because the target has not been reached after only 11 complete years. Financial growth rounds according to reality, not convenience. The question asks for total income, so calculate a geometric sum rather than only the 20th day's wage. Doubling begins harmlessly at 2 cents and ends by making payroll reconsider its life choices. The terms of this sequence represent the interest paid each year, not the unpaid balances. Because the principal decreases by $200 each year, the interest payments decrease by a constant amount. Add the 6 interest payments using the arithmetic sum formula to obtain a total of $336. These formulas summarize the main tools from the lesson. Model selection comes before substitution. Identify the pattern, decide whether the question asks for a term or a sum, and check the index. A formula used thoughtfully is a tool. A formula used randomly is decorative algebra. Approach each problem systematically. Identify the known values, choose the model, select the correct formula, and interpret the result. The goal is not to memorize isolated tricks, but to recognize repeated structure. Once the pattern is visible, the sequence usually stops pretending to be mysterious.